In addition to firewalls, there are also network intrusion detection systems. These are programs or devices that analyze data sent over the network in real time. On the basis of predefined patterns or anomalies from the baseline, they notify the user or autonomously take preventative actions. The simplest network intrusion detection systems analyze traffic against certain characteristics. Some programs create packets in a way that differs from the RFC standard. The foremost example of that is a TCP scan called the Xmax tree, which has the flags in the TCP header set in a nonsensical way. No host would send packets with flags set that way. Another example is the null scan. In this case, all of the TCP header flags are turned off. Network intrusion detection systems analyze packet headers, looking for anomalies. Thanks to that, they can identify a program which an attacker used, for example, to perform a scan. Each of these programs corrupts packets in a distinctive way. More and more network intrusion detection systems in use are intelligent systems. They learn the behaviors of the users of the network they protect. A system in the learning mode collects data about the user's activity in the network. Based on this, it creates a signature. We're not talking here about the signature in the sense of the combination of two header fields. Rather, it may include information that, for example, a user John Doe receives more data than he sends. The ratio of packets downloaded to the packets sent is 3:1. In addition, he connects to 4 favorite servers and works usually between 9 a.m. and 4 p.m. If the same user starts sending data at 11 p.m., downloading very little, and in addition sending the data from a database server which he has not connected to before, his behavior will be inconsistent with the characteristic calculated beforehand by the intrusion detection system. This is how intelligent intrusion detection systems work. This functionality is developed as part of an intrusion detection system called Snort, which has become sort of a standard. Having discovered a suspicious situation, that is, a packet matching an attack signature, or the one that doesn't match a user's characteristic or network traffic signature, the response of the detection system can be passive or active. A passive response consists of recording the attack and signaling it to the administrator. An active response is more interesting. In an active response, the communication channel is immediately interrupted as a result of an interference with the TCP session. Previously, we mentioned that more than 90% of the internet traffic and traffic on local networks uses the transport layer of TCP, because it's reliable and guarantees packet delivery. The session can be terminated by the commands of fin or reset. Discussing network intrusion detection systems, we should mention traps they use. Such traps are called honeypots. These are special systems run in order to attract attackers. One of their main advantages is that they are not production systems. They are configured to run certain services, but in fact, they do not provide any services useful for the network. This means that any attack attempt can be easily identified. Each connection attempt with a honeypot is suspicious. In a perfectly configured network, no one would try to find a database server by trial and error and then connect to it to read some data. Each user connects to the server dedicated to a given program. With a honeypot enabled, it's easier to analyze suspicious traffic because you don't have to filter out regular traffic. Each session established with the honeypot is suspicious. Despite numerous advantages, network intrusion detection systems and firewalls have their limitations. Here's a relatively recent story. It happened a couple years ago, which exemplifies these limitations. It was a 4-way handshake. It was publicized by the Breaking Point Systems Company and the NSS Labs Research Group. Let's start from the very beginning. The TCP, which is a session protocol, initiates the communication through a handshake process, which involves establishing a session. The RFC 793 describes the entire process in detail. It should proceed as follows. The initiator sends the SYN packet in order to synchronize sequence numbers. After receiving the packet, the recipient sends an acknowledgement message. For a TCP packet, this means sending an ACK flag. The recipient then sends its own synchronization packet. Usually, this flag is sent along with the previous one in a single SYN ACK packet. The initiator confirms receiving the packet by sending the ACK response. At this point, all needed information has been exchanged. Both parties know the sequence numbers. They can now reliably exchange data. In Section 3.3 of the RFC 793, this process is described slightly different. According to the document, the client, the initiator, sends a SYN packet. The receiver acknowledges it by sending an ACK packet. Then it sends its sequence number in a separate packet. Having received the SYN packet, the initiator acknowledges it by sending its ACK packet. Thus, the RFC describes session establishment as a four-stage process. It requires the exchange of 4 messages rather than 3. The issues the creators of firewalls and intrusion detection systems face is that their products are suited for the current situation. Because it's customary to establish a TCP session using 3 packets only, firewalls and intrusion detection systems assume that this is the only way to establish a TCP session. The RFC standard, however, is different. Firewalls are not universal mechanisms that always act in a predictable way. They are configured with specific situations in mind. If someone can look at the situation from a different perspective, and hackers are people who can easily find a different perspective, then the assumptions underlying the design of a device turn out to be wrong. The entire device will prove ineffective. We'll show that in a while.